All right. So the first day that we did this, we kind of did it more by hand. We used the formula. Said if we had so many objects and we wanted the, how many successes would we get exactly? You always say maybe we'd exactly get 2 out of the 5 successful. And then we would have to take the probability of success to a power times the probability of failure to a power. And I kind of show you how we did that before in Algebra 2, how we kind of did that even in advanced math, how we jumbled it up there, but the formula just made it so much easier. It was much more straightforward. But on your homework, I believe you had some that said at least this many, or at least fewer than this many, or stuff like that, which are a little bit more difficult because binomial is exactly this many. So you have to manipulate things. And so so we see here in this first column, we kind of see, our n values, and what do those stand for again? Yeah, how many trials? So maybe 2 trials, 6. All I went to is 6 up here, but how far did I go for you in your little handout? I went to 20. Obviously, is there a bigger table than this? Yes. I'm not going to give you anything over 20. And then how come the x's have different numbers in them then? How's that work? Like right here, x is 0, 1, 2, 0, 1, 2, 3, 0, 1. Those are possible, right? That's how many. So for here, if you're saying there are 2 trials and exactly one of them is successful, you would use 2, and then inside of 2 you would use 1, right? Or maybe if you were at 5 and there were 5 trials and you wanted exactly 3 to be successful, you would use the 5 and the 3 as your basis, okay? And then what are these numbers up at the top here? They don't even label that. There's just a bunch of numbers. I mean, what is that? What color? I don't know. Blue? You think that'll be too light? I don't know. Dark blue? I think that'll cover it right up, but let's find out. Yeah, that's just horrid. You can? Okay. So what are those numbers there? Those are kind of your probabilities. Okay. So what do you think? Is that believable then? So what is this? Who can kind of translate that number right there? What is that number? Can you go backwards from the table and give me what type of problem we're talking about? If you can do that, then this table will be very helpful. But I know it's been a weekend, so maybe. So if you have 2 trials and you want exactly 1 success, you have an 18% chance of that happening. But what was the percent of success to begin with? You had a 10% chance of it being successful. Where'd that number come? Did I just make that up? Yeah, it's right up top, right? So what you're kind of doing is, and maybe I'll pick a different color this time. Is light blue going to work? I think that's still going to be. We're just going to go with something like that maybe, huh? You're basically putting that and that together. Does that make sense? So 2 trials, exactly 1 success, and the probability of success in 1 trial was 10%. Do you believe that? So if you only did it once, probability of success is 10%. Probability of success of this happening is 10%. And you did 2 trials. That's the probability that exactly 1 will be successful. That's the probability of a success. But you're doing 2 trials here. And you want only one of them to be successful. Is it possible that both are successful? Is it possible that none of them are successful? So let's just take a look at this. Maybe this will help. If you add that up, that's 1. Because you're saying there's a 10% chance that it's successful, right? So they're saying that there's a 10% chance of something. Maybe it's the surgery one, or the, I don't know, did we do like a roll of the die or something? Didn't we do that one? And to get a 6, wasn't it? Out of 3 of them, we wanted only 1 6, right? So here they're saying if you did something twice and the probability of success was 10%, do you agree that having it happen never is going to be the most likely? And is it? Yeah. Having none of that, what you wanted happen. Then they're saying if you want just 1 of them, you get that. If you want 2 of them, you agree that that's, 2 out of 2, that means both of them work. Is there a really good chance of that happening? Okay. So if you said at least once, you would add those two together. Yes, it can make those easier, yes. The at least or this many, but I'm going to show you another way that should speed those up as well today. Okay, so do you understand kind of where the numbers are coming from on the table? Well, then let's go and actually use this table and solve the problem. All right. So 50% of working adults spend less than 20 minutes commuting to their jobs. Do you agree with that? You think that's probably fairly true? At least around here, maybe, right? Yeah, maybe in bigger cities, but they're saying 50% of workers. So obviously, some have to do more than that, right? In bigger cities, just because of how long it takes to get anywhere, that might be a slightly different number. But 50% of working adults spend less than 20 minutes commuting to their jobs. If you randomly select 6 working adults, what is the probability that exactly 3 of them spend less than 20 minutes commuting to work? Well, let's pull out the most important parts. And so what are some of the more important things? Well, basically, is 6 important? Yes. Is 50% important? 20 minutes? Am I going to use that in my calculation? No, and I'm not going to use it. And if you do, you're going to have some problems, okay? And what's another very important number? 3. Okay, so you say 6 is important, you say 3 is important. You're telling me that 20 minutes really is insignificant in the calculation. Obviously, it's significant to the people that did a survey or whatever to figure this out, but not to us. And 50% of working adults spend that much. Okay, so can we kind of categorize those or no? Do you think we can figure out what those are? Well, what are some of the important things? N is important, right? Number of trials. There are 6 trials. Very good. X, I'd say these are probably the 2 most important, right? Well, not necessarily most important, but there are 6 trials. And exactly how many of them would I like to be successful? 3, because I want to know probability of exactly 3. And what's probably the other, what's 50%? Really, in this particular problem, it is P, but it happens to also be, in this problem, Q, just by happenstance, right? Because how do you figure out Q again? That's failure, right? So if 50% are a success here, obviously the other 50%, right? But basically you do 1 minus P, right? The complement, and just happens to be, wow, that's not really a 5, is it? Just happens to be 0.5 in this one as well. So knowing that information, let's go. So you have that written down, right? Let's go to your tables. And let's see if we can figure that out. So N is 6. So that's where you kind of start. So N is 6. So I'm actually going to go down to this bottom one, right? So N is 6. We're going to talk about these. And the one I'm concerned with is 3. So you'd agree, this is kind of the one that I'm most concerned about. I hope I kept it fairly straight, did I? Not too bad, right? And the other one that I'm concerned with, y 0.5. That's your probability, right? Okay. So 0.5. What's the answer? 0.312, 31.2%, right? 0.312. Now, as it was said, this table can make the, at least, or it makes that a lot easier. You just start adding stuff up, right? I mean, so that saves you some time on those. Okay. So any questions on that? I hope you do see some symmetry, at least within 6 in there, especially the even numbers. You should see some symmetry within the numbers. It goes from 0.016, 0.094, 0.234, 0.312, 0.234, 0.094, 0.016. You should definitely see some symmetry within the numbers. Okay. At least on the 50%, you better. Okay. And again, you should still see that it kind of, yeah, there's a pattern, just trust me. Okay. So any questions on that one? All right. Now on this next one, the data was kind of old, so I figured, why don't we come up with a percent? So what percent of small U.S. businesses do you think at this time has a website? I think the data I had said 25%, and I think it's much higher than that now, right? Small U.S. businesses that have a website. If you randomly select, so let's just come up with a consensus in our class about how, I think we agree it's more than 25, right? So small U.S. businesses. Again, does it kind of depend on how they categorize small? I'm sure there is some formula out there to categorize what counts as small. It's probably number of people served or amount of revenue would be my guess. So I'd say higher than that probably. I think it might not be 89.
Oh, 85.
So should we go, let's make sure that it's something we can find on this table. So I don't think 89 is probably a way we want to go. So should we go 75%? Let's go kind of the complement of what they had. So we'll say 75%. And if you want to find out what that is, you can go ahead and Google search that if you want. But I kind of wanted to see what kind of information you would give me on that. And I'd say we're probably pretty close. So 75%, well then what did we just come up with? What is 75%? That's P. Okay. So if we were going to the formula, what would Q be? If we had to use the formula, Q here is 0.25, right? Very good. And so obviously the things, if we're going to use the table, I mean, those are the important things, are N, X, and P. And really, aren't those the same things that were important when you're using the formula? Because you could find Q easy enough, right? And so N is, how do you know it's 10? Yeah, that's the number of people we're going to ask. So that's kind of like your number of trials, right? So 10. And what exactly would I like to know? 4 of them. So we're saying 75% of them do, and if I ask 10, I want to know exactly 4. Do you think this is going to be a pretty high probability? I know some of you probably already have it. Or pretty low? Okay, I've been told pretty low. Why pretty low? Because some people say, hey, 4 out of 10, isn't that going to happen a lot? No, what's going to happen? 6 out of 10 is going to happen a lot. 7 out of 10 is going to happen a lot. 8 out of 10 is going to happen a lot. So do you understand the difference in the questioning here? They're saying 75%. So is that very probable that only 4 out of the 10 are going to actually have that? Now, what if it was back at 25%? Yeah, that is probably pretty good, isn't it? 4 out of 10. It's a lot better than what we're going to have on this one, right? So let's go back then. So obviously these little highlights aren't going to be very helpful anymore. And so we're going to have to do that again. So should I stick at the 6 though? Well, in fact, I don't even think I have this one. Nope, I don't. So when you went and you did have to go to 10, right? And you go down. I have one right here. Where's 10? There it is. And we have to go to N, X being 4. And then we go over to 0.75. And if you do that here, you get 0.016. Is that lower than you thought? Well, that's a little lower than I thought it was going to be. But so 1.6%. Wow. That's interesting. So let's go back to the one they gave, 25%, and then 4. Well, that's even lower than I thought. I guess that's not that bad. 0.146, right? So 14 point, that's an incredible difference though. So let's face it, which number is going to probably give us the best answer here? Either between 7 and 8 somewhere, right? So if we go down to 7, let's just investigate that. 7 and 0.75. Ooh, how about 8? Are those lower than you anticipated? 0.25 and 0.282? But you got to realize they distribute the numbers over all of it. So 25% actually happened in there? No, that's believable. Okay, so again, the tables can be very helpful. So now what we're going to do is we're going to go use the calculator. All right. And the results of a survey indicated that 58%. Oh, so I think we already see the benefit of a calculator. Is that table going to give us this answer? Why not? 58%. So could I get close to this answer? Because we would use 0.6 probably. If we can get close, but we wouldn't know exactly. And let's face it, if they made the tables that exact, you'd be there. That thing would be huge. And it's big enough as it is already. So here's the definite help of a calculator. Of American households own a gas grill. That's probably pretty good. I bet you, because I think a lot of people prefer charcoal or just don't have one at all. If you randomly select 100 households, what is the probability that exactly 65 will own a gas grill? So before we go to those calculators, what do you think? Based on what we just kind of saw here, is this going to be good? So it's 100 households, and I want exactly 65. And we're told that 58% do. Because let's face it, we just found out that exactly was 25%, right? On that last one, I said, what if it was exactly 7 or whatnot? And we found out that was only 25% because it gets distributed so much. So we're thinking this is small? So yeah, probably. It is, but is it close enough? Yeah. The biggest number of that's going to be at 58, right? If we actually found that. And that's probably not going to be that big because, again, we have to distribute it to all those other possibilities. Okay, so let's figure out our things here. What did we say was important? We said n was important, right? And what else? X and p. Because let's face it, if you got p, you got q. I mean, it just goes together. So n is 100, x 65, p 0.58. And again, if you want q, you can get that, but the calculator doesn't care either. It's kind of like the table. It knows you can get q. All right, so now let's see if I can remember where it is. I'm pretty sure that it is actually under stat. And then I think I'm wrong. Yeah, oop, where'd it go? It's not one of the tests, though. That's the thing. Oh, doop, 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 doop. I'll find it. Don't worry. I did. I actually did all of these, and now I just forgot where it was. Yeah, I could just do that. But... Oh, hello, distribution. Yeah, that would be smart. Why don't we hit that button? So DSTR has distribution right above it, so that would have been probably the smart place to go. And there are a lot of them, as you notice. The one that you want, oop, I went too far. So again, you hit second, and for me it's variables. There's distribution right above it. And here's binomial, right? You see that? Binomial, probability, distribution, function. Okay? That's what that stands for. Okay? CDF is cumulative distribution function, which might be handy for those at least and less than problems as well. What that does is it adds it up to that number you give it. So it's cumulative. It does it nice for you like that. So perhaps we'll take a look at one of the problems from your homework and use it on there. Okay? So that's what this. So it is also binomial. That's good that somebody asked that. I was waiting. The CDF is a cumulative. It'll add them all up for you up to say the second one. It's not exactly 2. It's 0, 1, and 2. It adds them all up, which is very nice because it's kind of like the tables. You can add those up easy enough, right? So binomial, probably. So what do you think we put in first? Nope. Nope. N. Now, from those that have worked with the calculators, how do you tell the calculator that you're going to give it something different now? Comma. That's a lot of programming does that. You put commas in between what are called parameters. Comma is right above the 7. And now what you do is you put in P. So you might want to write in your notes. It's where it is and how you type it in, right? So 0.58. And what do you think next? Comma, very good. I thought somebody was just going to tell me the 65, but you didn't. Now, what are you going to put? 5. Nope, you don't even have to do Q. It has formulas to take care of that for you. That's all you got to put. That's pretty simple, isn't it? It's almost the exact same knowledge you needed for the charts. If you told me you thought this number was going to be small, right? Wait, so 3%? So what if we do actually hit the binomial cumulative distribution function and put the exact same numbers in? Yeah, it's going to do all of them from 0 to 65, and it's going to add them up for you. So do you think that's going to be what? More than a quarter, more than a half, more than 75% of them? What do you think? Okay, so let's just go ahead and try that then. Where do we go? Let's go to distribution, and I think it's letter B, so I think you can actually do that. There we go. Well, let's go ahead and do the same problem, but say we wanted to know 65 or less, really, would be the question here, right? Because you're including 65, right? So do all the same thing, 100, 0.58, and 65, right? Exact same stuff. This is saying now you're going to take the answer for if you put a 0 in for x and a 1 and a 2 and a 3, and put them all in and added them out. That would take forever, right? And even, let's face it, in the table, if you had a table this far out, that would take forever too, adding all those up. So this just does it for you. And now, what do you think? I know some of you already did it, so don't answer, but do you think this will be more than half, less than half, more than a quarter, less than, what do you think? Give me a range that you think maybe this would be in. Oh, you already did it? Whoa! 93.7% chance. Does that make sense? Well, let's face it. Is the probability of somebody having 66 or 67 or 68 or 69 all the way to 100, are those very good chances? Not really, are they? Because you got to be pretty close to that 0.58 for this to work out well. And remember, the only contribution that 65 gave was that. So did that really contribute very much? Not really. Okay. So that's how that function can be handy. So why don't you try example 4 right now on your own using this calculator here and see what you get. So obviously we answered this one already, right? We answered this was what, about 3% or 0.029 or about 0.03-ish. Okay. So go ahead and give that one a shot. All right, let's see how you did. All right, what do we got here? What is our parameters here? N? 50? X? Remember, that's the random variable right there. And 0.71. And you type that in, so it would look something like this. To save us time, I'll just do it like this. 250, comma, 0.71, comma, 178. And you hit enter. Approximately 0.056, so 5.6%. Surprised by that answer? Again, it's saying exactly that many have that. That's what you have to really get in your head, that it's saying exactly that many people would have more than one topping on their hot dog. Okay. A survey indicated that 41% of American women considered reading their favorite leisure time activity. You randomly select 4 women and ask them if reading is their favorite leisure time activity. Determine the probability that exactly 2 of them respond to yes. So, what are we going to do? Well, we're trying to find out basically that you give a 2, right? So you could kind of say, you could write it like this if you wanted to, probability of 2, right? You could put it into that big long formula. This one, can you use the table? Not very well, right? Because 0.41, right? But as far as the numbers are concerned, they would at least be on your tables, right? But except for the 0.41. And so that's where using the calculator can save you a ton of time. This is exactly 2. All right, so we know that N, X, and P are the most important. And N here is 4. Right there. X is 2. All right. So let's go ahead and type that in. This might be faster, not even going through all those things, but we can just do it just so you get used to using it there. So we got to bring that up again. So distributions. Yeah. I'm pretty sure there is. So I erased everything already though. What is it? 0.41 and 2. Right? Did I hit the right function, so to speak, the right program? Yeah. PDF, probability distribution. I'm not trying to add them up. I just want to know one of them. And there's 4 of them. Chance is 41%. I want to know what's the probability that exactly 2 of them prefer reading, right? Surprised? And you got to think, how many options are there for the random variable? 0, 1, 2, 3, or 4, right? So there's only so many options. And so did you notice when there was 100 options or 250 options? That's a lot to spread out all your options on, isn't it? And they have to all hold some probability. Okay? And so here, there's not many options. And so some of them have to hold a pretty big value, right? So I would guess that 1 and 2 are going to be your higher values. 2 is probably going to be higher because it's closest to the probability of success. Is 3 going to be higher or lower than 2? It's going to be a lower probability, right? Because it's further from that probability. And all 4 of them? Pretty small, right? And 0 of them? Also pretty small. So do you understand what I'm trying to get into your heads here? Okay, so the next question is saying at least 2 of them respond. So that's saying 0, or is that saying 0, 1, and 2, or is that saying 2, 3, 4? Huh. At least 2 of them. Well, is CDF going to tell me 2, 3, and 4, though? Yeah, how are we going to do that? So do you agree that saying at least 2 is saying that 2, 3, or 4? You agree with that, right? So could we do the cumulative for 0 and 1? And subtract it. And if we do just 0 and 1, what answer are we finding? Aren't we finding C? If we do it that way? Now, if you have to do it by hand, you have to find the probability of 2, which we already did. We know that answer. And then find the probability of 3 separately and find the probability of 4 separately. You could do it that way and then add them up. Or on the table, if this was an acceptable table one, you would add them up. We don't know that. So I would say should answer C first because of the technology that we have. So let's do this one. This is saying that X is basically equal to 0 or 1, right? Isn't that what it's saying? Your random variable is either 0 or 1. And I would like to add them up. Do you agree with that or no? Is that making sense to everybody? Okay. So let's go use that cumulative distribution function. And unfortunately, we will have to go in and get that distribution function. Right there, right? And it's still 4, right? It's still 0.41. But now, do we put 2 in? Why 1? Because we don't want 2 included, right? We want to know 0 and 1 and leave 2 on that other part that we're going to subtract and get, right? And you can actually just put the 1. You don't have to put 0 and 1. It's just saying when you put 1, it's assumed that 0, 1, all the way up to the number you put, okay? And it'll add it up for you. Are we expecting this to be really tiny? Again, it's a small grouping there. It's, so there's going to be some weight to that, because 1 is one of the numbers that's pretty close to the 1 out of 4 is pretty close to the 0.41, right? And so let's say that's 0.46, okay? So if we say that that's 0.4 or 0.458, wherever you want to round, I don't really care. I'm sure the assignment will tell you where to round. And so that is your answer for, so what are we going to go, 0.4, what do you want to do? 0.46 is this answer, right? And do you agree that if I put B and C together, that we take care of the entire sample space? 0, 1, 2, we get them all, right? And so they are the complement of each other in this particular problem. Be careful, though. I might do something like fewer than 3 or something like that, and then you got to do the problem slightly differently, okay? So this one over here, you just do 1 minus that, and you get 0.5. Well, the way we rounded to be 0.54, right? If we rounded this way. And we're almost done. Any questions on that? Is it making sense? Yes. Exactly. If you put 2 in there where I put the 1, it would be 0, 1, and 2, which is what we didn't want here because we wanted fewer than 2, which in this case is just 0 and 1. Those are the only two options that were less than that. So whatever number you put here, it's going to go all the way to that number. So it all goes all the way to 1 and includes it. Okay? It doesn't stay less than it, unfortunately. Okay? Because that would be nice for these types of problems. Good question. So this one here, I've given you some nice little shortcuts. When you have a binomial distribution, the mean is just n times p. How come it's mu, by the way? Don't we know everything? We know. It's however many trials is the population, right? There you go. Variance, which is sigma squared, is just n times p times q. Standard deviation is obviously the square root of that. So if we know, let's try and figure out, what do we need? We need n. Do we even need x? We don't even need it, right? Because it doesn't matter. But n and p are the two things that you need, because once you get p, you can get q. It's all you need to get these three things. So n. How do you know that? Oh, are you sure? Keep reading. Yeah, let's go to the knuckles here. In June, 30 days in June. So there's 30 days in June, and P is 0.57. There's no guarantee that it's 0.57 because I could have said, what's the probability that it doesn't rain or something like that, right? And so to get the mean, which is mu, you just take n, which is 30, times p, which is 0.75. That's the average. And that's no, it's not really, I guess it's kind of approximately. What, 17.1? And again, variance, is that a number that really helps us all that much anyways? The only reason you get variance is so you can get what? Standard deviation. So let's just go right to sigma there. It's the square root of 30 times 0.57 times what? 0.43, because that's q, right? Let's just jump right to standard deviation because it is more usable here. Approximately 2.71. Once again, here comes the question, what does that mean? Pardon the pun. Yes? So on average, how many days is it going to rain in Pittsburgh? In June? Nope. On average, how many days is it going to, does it say rain or does it say cloudy? So how many days is it going to be cloudy? 17. Fun place to live. 17 out of 30 is going to be cloudy. And if you picked any particular day, I would expect that within 3 days either way, it was cloudy. Does that help you understand standard deviation a little bit better? Okay. Okay. So I was kind of hoping that, but the nice thing about binomial is how easy those numbers are to get. Remember how long we spent doing standard deviation and some of those other things? Doing all those tables? But this is pretty nice. Okay. So any other questions?